All right, in this lab, we're going to look at composition and change. Okay, looking at how we take measurements, convert those, or calculate new things like density, how we classify matter, and how we decide whether a change is happening physically or chemically. So we're going to be going through 12 stations overall and trying to figure out some things about each one. First up, we are going to be looking at some aluminum samples. So I've got here a piece of aluminum foil. You've got a little aluminum cube. Okay, it's painted red, but you can see kind of the aluminum silveriness on the corners. We've also got an aluminum cylinder like we would use for the density calculations we did in a different lab. Okay, now in all these cases, okay, whether you're dealing with aluminum as foil, cube, cylinder, whatever, aluminum is a pure substance. It's an element you can find right off the periodic table. Okay, it stacks up something like this. Okay, now we can see that there's just one atom of one element of aluminum. So there's no bonding, two atoms together of the same element. There's none other elements kind of jumping in here. We're just looking at this pure version of aluminum. Okay, and as we continue to stack those single elements over and over and over again, we get a structure that's pretty closely packed, which can tell us a couple things. For one thing, it can tell us how we classify the pure substance of aluminum, whether it's a monatomic element, a diatomic element, or a compound. Okay, it can also tell us something about the density. So I have different size pieces of my aluminum here that all have different masses and volumes, but whether I'm using the piece of aluminum foil or the cylinder here, whether I have more mass, less mass, which way it's spread out doesn't matter, since I'm going to be stacking up the atoms as close as I can get them. More mass means more volume. More volume means more mass, and vice versa. A smaller piece is going to have less mass, less volume. So by the time I calculate my density and take mass divided by volume, I should get the same number, okay, that same ratio of mass to volume. Okay. Now we can also make aluminum go through a change at this station. I've got a little bit of aluminum foil in the bottom of this cup here. I've also got a chemical called copper sulfate, or CuSO4. I'm going to add about 20 drops in here. Looks about good. Okay, we're going to try and figure out what kind of change is going on here and what gives it away. So to get this going, I have to kind of scrape at it a little bit. Okay, so you can kind of see there's that blue liquid in there, and I'm just going to kind of scrunch it in there. Now, if I get this close enough, you might be able to hear. There's a noise coming from this. Okay, and we're getting a change here. This ends up being a chemical change, but there should be some clues that tip us off to the fact that this is a chemical change. So, if I get this a little bit closer, okay, you might see that the color has changed. I've gone from having this silvery aluminum color to, I've got some spots of like reddish brown in here, which is kind of interesting. Okay. Now also, you're going to have to take my word for this, but the bottom has gotten a little bit warmer. It's gotten a little bit hot. Okay, if you heard that kind of sizzling noise, okay, that was from heating up that liquid, okay, and getting that reaction to go. Okay, so we got a couple signs of a chemical reaction going on here. Okay, so that's first station. Next up, speaking of density, I'm going to be looking at 70% rubbing alcohol, also known as 70% isopropyl alcohol. Okay, what the 70% means is that 70% of this is isopropyl alcohol. That's a chemical. It's a pure substance. Okay, and the other 30% is water. Okay, now kind of look at it in here. It's not like I can pick apart the different parts of this mixture. I can pour some out into a beaker and show you. And I also want to figure out the density of this mixture. Okay, so I want to get 20 milliliters of this rubbing alcohol. Turn on my scale. Okay, but I want to make sure that I'm not including the mass of the beaker. So once my scale loads, tilt this down a little bit. Okay, I'm reading 0.0 grams. I'm going to put the beaker on the scale. So it gives me the mass of the beaker. I zero it out because I don't care about that. And then I can add in my rubbing alcohol, about 20 milliliters. Okay, it's a little bit over. I'm going to pour a little bit out. That's a little better. All right. Okay, now, as this is in the beaker, you can really tell this all just kind of looks like water. So you can figure out whether it's a heterogeneous or a homogeneous mixture. Okay, now this 20 milliliters of rubbing alcohol has a mass of 17.1 grams. I'll try and get a little bit closer to the scale so you can read it. Okay, so if I have the mass and the volume of this rubbing alcohol, I can calculate the density. Density is just mass divided by volume. So my 17.1 grams divided by my 20 milliliters should give me the density of this 70% rubbing alcohol. Depending on how much rubbing alcohol you got in your beaker, answers might be a little bit different, but they all should float around the same answers. Okay, so I've got that poured out. Turn my scale off and move my stuff. And we can move on to the next station. In this next station, I'm going to model a chemical change. Okay, between these chemicals. Okay, this guy right here is CH4. Okay, also known as methane. Okay, these guys are O2, or we call them dioxygen. Okay, this guy is CO2, or carbon dioxide. And these guys are H2O, or water. Okay, so in this case, we're using each sphere counts as one atom, and each color counts as one element. So black represents carbon, white represents hydrogen, red represents oxygen. And each one of these spheres is an atom of that element. Okay, so the reaction that happens between these guys looks something like this. Tilt this a little bit up. Set this down here for a second. Something like this. Okay, so one guy, my CH4, plus two O2s can make one CO2 and two H2Os. Okay, now this is representing, again, a chemical change. We can look at each of these substances and we could figure out what kind of pure substance it is. Like, for instance, methane, okay, CH4, again, looks like this guy. Okay, we could figure out whether this is a monatomic element, a diatomic element, or a compound. Okay, we can also just look at this and figure out how this shows a chemical change. Okay, so these little models we call snatoms because they're atoms that snap together. Okay, end up changing from the CH4 and the O2, and on the other side here we make the CO2 and the H2O. Okay? Those are totally different chemical formulas, which means totally different chemical recipes. These are different substances. Okay? And that's kind of the key about a chemical change. All that really matters is that we have to have different substances in the process. Okay? Now, a lot of times in the lab, we don't actually see anything that would indicate this going on here. You know, we usually have models that we've kind of used to show something that chemists have already figured out over the years. You know, knowing that methane looks like this and oxygen looks like this, but in the lab we usually don't see something that represents the atomic level, okay, for our eyes, unless it's written out for us or we have models like this. So what does this reaction look like in real life? Okay, well, I'm going to bring this over here. Okay, so this is a Bunsen burner. We use it to burn gas, typically natural gas, so like methane is one of them, and also some propane. Okay, I've also got a striker here that makes sparks. Okay, it's not about how fast you go, it's about really pressing that against that plate there, getting the flint to strike. Okay, so I'm going to go turn on the gas. I'm going to light the Bunsen burner, and we'll see what this chemical change looks like in real life. I point the valve towards the hose. That means the gas is flowing. I can hear a slight hissing noise as the gas is coming out. Okay, I just have to light the gas. There we go. Okay, so this is a flame, all right? This is a sign of a chemical reaction, okay, where we've got, it's hot. We've got some heat coming out. We've got light that we can see. That's the essence of a flame, all right? It's sort of the clues of a chemical change going on here. In this case, between the methane gas and the oxygen in the air. We just kickstart it with a spark. Okay. So that was our combustion model station. Let's move to another one. What I've got here next is a jar of trail mix. Okay, so I've got peanuts in here, I've got some M&Ms, I've got some raisins. This is from a couple of years ago, so it's not good to eat, but we can still use it to kind of observe. Okay. So just by looking at it, you can probably tell whether we would call this a pure substance or a mixture. Okay, is the trail mix a pure substance or a mixture? Okay, and also based on looking at it, you can figure out if it is a mixture, what kind of mixture it would be. Is it homogeneous or heterogeneous? Okay. Now you can also imagine, I'm not going to do it, but you could also imagine if I were to dump some of this out and smash it and crush it up, would that be an example of a physical change or a chemical change? Okay, and you can think about our last example with the combustion model where we had substances turning into something totally different, okay, through that process. You can think about if this stuff is really different or if it just looks different. Okay, so that's the trail mix station. That was a pretty fast one. Next up, we have fluorite. Okay, our fluorite station shows off a mineral called fluorite. Something like this, got a nice green color. Okay, its chemical formula is CaF2. Okay, that means it's made of the elements calcium and fluorine. Okay, Ca and F, calcium, fluorine. Okay, so thinking about that composition, you could think about whether this is made of just a single element or if it's a compound made of multiple elements. All right, it would be hard to tell just by looking at this. Pure substances can be a little bit misleading. We a lot of times think of pure as single, one thing, but pure substances can be made of different elements, like compounds. Okay. Now you can also try and figure out whether this is a pure substance or a mixture. In this case, if you get kind of an impure piece, like this guy, sometimes you've got some little bits of stuff, other rock fragments that have been stuck in the sample, but we're considering just the fluorite here, okay, not other little bits and things that might be stuck to this. So just the piece of fluorite here is what we're looking at. Okay. Now, one of these pieces of fluorite has a mass of 67.3 grams and 21.16 milliliters of volume. Okay, so if I want to figure out the density of fluorite, density is mass divided by volume. Mass was 67.3 grams, volume was 21.16 milliliters, so I can just divide out my mass by my volume and get my density. Next up, we have a rotting apple. Ooh, exciting. Okay, now, if we look at this, you might be able to find some signs of a chemical change. Now, there's some air in the bag, but that air was already in there. It's not like a new gas has been formed specifically. It doesn't really feel warm or cold. It's about room temperature. It's about what I would expect it to feel like. Okay, you might notice kind of a discoloration, sort of a whitish color, like the lighter yellow is sort of what it would normally be like. You got some darker brown here, so that might be a good clue. Okay, now, in general, you could also figure out what state or phase of matter this is in, solid, liquid, or gas. Keep that. I've also had this sitting out for about 1.88 days, so we could convert that to minutes to see how many minutes it's been sitting out. We can't do it all in one step. We need it in 2 steps. Okay, we would have to go first from 1.88 days to hours. Let's see, there are 24 hours in a day. Remember, whenever you're converting units, doesn't matter which units you're converting to or from, okay, we always want to get rid of the old unit, which means we're dividing by the old unit. We always want to pick up the new unit, and we multiply by that new unit to get there. So if I am trying to get away from days and I want to get to hours, I want to be multiplying by hours and dividing by days. Well, 24 hours in a day, so I want to multiply by 24 hours and divide by 1 day to convert that into hours, from days to hours. Now, if I wanted to go one step further and convert to minutes, okay, well, 1 hour is 60 minutes. Now, hours is the unit I want to get rid of. Okay, so I'm going to take another step and work out the math. Again, multiply by what I want the new unit to be and divide by what I want to get rid of, that old unit. Okay, always put the old unit on bottom, always put the new unit on top. So that was our rotting apple station. Next up, this piece of rock. This is granite. Get this a little bit closer. See it nice and close. Okay, now just at a first glance, you can tell this is a mixture. Okay, now also, because you can just look at it and tell this is a mixture, you can tell it's a specific type of mixture. So, what is this, a homogeneous or a heterogeneous mixture? Okay, now these different minerals you can see are mostly quartz, potassium feldspar, and biotite. Okay, and each of those is made up of a bunch of different elements. Okay, so for instance, quartz is made up of SiO4. Okay, that's a silicon atom, and 4 oxygen atoms, kind of all stuck together. So it would look something like this. This is what I used for methane earlier, but it's very similar looking. So this would be a good example of kind of what our SiO4 looks like in our quartz. So what would that be? A monatomic element, a diatomic element, or a compound? Okay. Now, across these, there are also a bunch of different elements, okay? So in the quartz, potassium, feldspar, biotite, whatever, we have even more elements, aside from just silicon, Si, on the periodic table, or oxygen, which is O. We also have K, which stands for potassium, Al, which stands for aluminum. We have Mg, which stands for magnesium. We also have F, that stands for fluorine. Okay, so there are all kinds of elements packed into this rock in different ways. Okay, so you can use that to figure out what elements are in these compounds inside this rock, and maybe what's not in the rock. Okay, that was our granite station. Next up, I have a rusty iron block and a sphere, rusty iron sphere. Okay, now this was originally just iron. And if you look closely, I've kind of scrubbed off and polished this side so you can see the sheen. Okay, it's nice and smooth. Okay, but if you look at the other sides, if you've ever felt a rusty surface, it's kind of uncomfortable. It's kind of dull. It's got a reddish brown color, and I can feel it's rough. Okay, you can also see kind of on the corners here where it says catching the light. Okay, that kind of original silvery color of the iron. Okay, where the rust hasn't gotten. Okay, so we can figure out if this is a pure substance or if it's a mixture. Okay, now also, based on that difference in color, you can figure out whether this is a physical change or a chemical change. So, even though we're not seeing the rusting process and kind of in motion, in action, it's a pretty slow process, you can see the before and after. Okay, so on the corner here, this silvery bit, or on this edge that I've polished right here, okay, you've got kind of the before, and then on the flat edges, you've got the after, this sort of reddish brown, dull color. So you can use those to figure out whether this went through a physical change or a chemical change to get here. Okay, finally, this block has a mass of about 0.184 kilograms. If I wanted to convert that into ounces, it would be a little bit tricky because it would take two steps. Okay, kind of like the rotting apple changing days into minutes. Okay, I don't have a conversion unit that goes straight from kilograms to ounces, but I can go from kilograms to pounds. I can go from pounds to ounces. Okay, again, remember, always get rid of your old unit by putting it on bottom. That's the one you divide by. So first, I'll want to divide by kilograms and make sure I'm multiplying by pounds. Okay, I want a conversion factor that has pounds on top, kilograms on bottom, multiply by the top, divide by the bottom. Okay. Now, once I have that done, I want to convert to ounces, which means pounds is going to be my old unit I want to get rid of. So in the second step, you want to get rid of pounds on the bottom and get to ounces on the top. Look for a conversion factor that has ounces on top, pounds on bottom, multiply by the top, divide by the bottom. Not too bad. Okay, so that's our rusty iron sphere and block. Okay. Next up is another model of a chemical change. In this case, our chemical change is between H2O, water, okay, and how it changes into H2, which we call dihydrogen, and O2, which we call dioxygen. Again, red stands for oxygen and white stands for hydrogen. Okay, so our reaction looks something like this. Okay, where 2 bits of water are changed into 2 bits of H2 and 1 bit of O2. Now, just by looking at our model here, Okay, this is again dihydrogen. This is our H2. We can figure out whether this is a monatomic element or a diatomic element. Okay. Right. Now we can also look and see if mass is conserved here. In other words, do we lose atoms? Do we gain some out of nowhere? Or are they all accounted for throughout this process? Okay. Well, if I start with two of these guys, okay, let's see if I can get both of them at once. Okay, that gives me a total of 2 red atoms, 2 oxygen atoms, and 4 white ones. That's 4 hydrogen atoms. Okay, I end up making 2 H2s, which is 4 hydrogen atoms, and 1 O2, okay, which is 2 oxygen atoms. So everything is still there. The only thing that's changed is how we attach the atoms to each other, how we bond them together, okay, how we rearrange these into something different. Okay, now like the combustion model, we want to be able to see this in the lab so that we can tell it is an actual chemical change and look for the clues. So let's try it out. I've got some salt water here, and I've got a little bit of cup with tacks on the bottom of it. I also have a battery. Okay, this is kind of like the striker in this case. What's going to give us that little bit of kick to get the reaction going. Okay, so the salt in the water is just to kind of help conduct electricity through the liquid. Water on its own isn't all that good at conducting electricity, but with salt or other minerals, dissolved ions, however you want to say it, it becomes a lot better. Okay, so there's my salt water. I'm going to get this a little bit closer here. Point this down. Okay, I'm going to touch the battery to the tacks on the bottom of this cup. Hey, all right. Looks like we've got bubbles. Okay, so these bubbles are actually hydrogen gas. Okay, now the reaction tells us we should also get oxygen gas from this, but we don't see it. Well, if we are kind of following the trend here, if we're getting hydrogen gas out here, maybe we're supposed to get oxygen gas out of this other tack, but so far it's not doing much. Okay, well, what happens when you put together metal and water and oxygen together? Well, like we saw with the rusty block and the rusty sphere, you rust it. Okay, we corrode it or oxidize it. Those are all different words for kind of the same thing. So that's what's going on here. We don't see the little bubbles of oxygen because they immediately go and rust and react, corrode this metal tack right here. Okay, they don't even get the chance to escape as a gas, as little bubbles. They just immediately go and react. Okay, now we can't see the bubbles, but we can see kind of a product of this change as the color of the water starts to change a little bit. Okay, to kind of loosen it up, I'm going to switch the sides of this so I can push some bubbles through the other tack and hopefully break some stuff off here. Yeah, now I don't know how good my camera on my laptop is, but if it is, you'll hopefully be able to see that we're getting kind of a greenish bluish color in the water now. Okay, that's from little bits of corroded metal coming off of here and breaking off and floating into our cup. Okay, so we've got a couple signs, a couple clues of good chemical change that's going on here. So that's our electrolysis model. We call that chemical reaction electrolysis. Next up, we're looking at melted crayons. Okay, I've got a couple different crayons that were kind of melted together here. So from the top, it all kind of looks like one kind of gross sort of greenish brown color, but on the sides you can better see the different colors that used to be in there. Okay, so this started with 8 crayons of red, orange, yellow, green, blue, purple, and white, and then I had a double of one of those colors. I think. Yeah, I had 2 of I think the green crayon maybe. Okay. Now each crayon was about 4.8 grams. Okay. So we can figure out a couple things about this little beaker of melted crayons. You can first try and figure out if this is a pure substance or a mixture. Okay. Again, just by kind of looking at it, you might be able to tell. Now, this has solidified and it's back to being like wax, like a crayon would be. Okay, it looks a little bit different, but I mean, it's still wax. Okay, it's still that crayon material. So that might tell you something about whether the melting process and the solidifying back into a solid was a physical change or a chemical change. Okay, and finally, if I wanted to figure out how much crayon wax I have in here, if I had 8 crayons that were each 4.8 grams, I can do a little quick math to figure out how much mass in grams I had for all 8 of those crayons, if each is 4.8 grams. So that's my melted crayon station. Next, we're looking at these crushed and uncrushed cans. Not a whole lot super exciting. I mean, I just took one of these cans and I crushed it in with my hand. Okay. Now, at first glance, this looks like a pure substance, what this is made of, aside from the colors on the outside. I mean, it just looks like metal. It's just a metal. And you probably call this an aluminum can or a tin can or something like that. But its composition is a little bit more complicated. It's not just aluminum. It's actually also got magnesium and manganese in there, 2 other metals. Now, you can't tell just by looking at it, but it does have a total of 3 metals in there, maybe even some other stuff, depending on the special formula of the can that people produce. Okay, so you can use that to figure out whether this is a pure substance or a mixture. Knowing that composition of what's on the inside is really key for that. Okay, now the can itself, okay, is not flowing out onto the table. It's not escaping out of the air. So you can figure out whether it's a solid or a liquid or gas, what phase of matter or state of matter it is. Okay, and just by comparing these two, you know, again, this is kind of the before, this is the after. Okay. Did this go through a physical change to be crushed, or was it a chemical change? All right, so that was crushed and uncrushed soda cans. And we are on to our last station, where I've got a balloon. Whoop. Just about escaped from me. Okay, I've got a balloon here. Okay, now I want to know what the phase of matter inside the balloon is, a solid or liquid or gas. What is holding this balloon inflated? What's keeping it there? And what's this I'm trying to squish on the inside? Okay, what phase of matter, what state of matter is in there, solid, liquid, or gas? Okay, now to fill up this balloon, I didn't use a pump, I used my breath. Okay, so I blew out, I exhaled, okay, and I mostly breathe out dinitrogen and carbon dioxide. The carbon dioxide part's the one you usually hear about most. Okay, now in the thinner parts of the balloon, you can try and kind of look in here. Okay, but I mean, we can't see really a lot of gases anyway. Carbon dioxide and dinitrogen are both colorless. They're clear. They're see-through. Okay, and even as I breathe out, you know, I'm not letting out like a color of something. You can't see it. So that might be able to help you figure out what kind of mixture this is inside the balloon. Is it a homogeneous mixture or is it a heterogeneous mixture? If I can't see those different components, it all just kind of looks like one pure substance, or it doesn't even look like something because I can't see it. Okay. Now, this balloon, okay, has a volume of 1,240 milliliters. Okay. If I wanted to convert that to a nicer looking number, like in liters, I would have to move my decimal place. Okay. So I would need to look at a metric prefix chart that's got, you know, kiloliters, you know, regular liters, milliliters, and the ones in between like centi and deci and deca and hecto. And I'd have to look at how many spots I'd have to move to go from milli to regular liters, the base unit. Okay, however many spots I would move to go from milliliters to regular liters is how many spots I'd move the decimal place, and I'd move it in the same direction. Okay, so I can pretty easily convert this from 1,240 milliliters into liters if I just move my decimal point around in the right way. Okay, again, going from milliliters to liters. Okay, and that's the last station balloon breathed into.